Okay, this lecture is on graphs. It's probably going to be a little bit longer than our typical lecture. I'm just cramming a lot into one lecture. So what is a graph? A graph is a collection of vertices or nodes and edges or connections. And we generally write this as capital G equals, and then within brackets that look like less than, greater than signs, we list the sets V and E. Graphs are important in computer science because they efficiently model relationships and connections in data structures, networks, and algorithms used for solving complex real-world problems. Let's look at some terminology with respect to graphs. Um, we already used the word node. We also call these nodes vertex. Uh, each one is a vertex, or vertices is the plural, and they're a fundamental unit of the graph. We have our edges, which is a connection between two vertices. We say that an edge is incident to a vertex if the vertex is one of its endpoints. We say that two vertices are adjacent if they are connected by an edge. And we say a vertex is isolated if it has no edges. We also call this degree zero. So degree is the number of edges coming in and out of a node. Just talking about these definitions with a little bit of an example. I'm showing a graph here with three nodes and one edge. And from the definitions that we just talked about, we can say there are three vertices here, A, B, and C. The edge AB is incident to A and incident to B. The vertices A and B are adjacent, that is because they're connected by an edge. And vertex C is isolated because it has no edges. Let's talk about some other types of graphs or qualities of graphs. A loop is an edge that connects a vertex to itself. We see this often in communication graphs where we're actually modeling real communication networks that do have loopback circuits. It's possible for a graph to have multiple edges between the same pair of vertices. A simple graph, though, has no loops and no multiple edges between the same two vertices. And we're going to be mostly concerned with simple graphs. So again, by example here, vertices B and C both have loop edges. There are multiple edges between vertices A and B, and hence this is not a simple graph. Now when we talk about graphs, we can broadly characterize them into undirected and directed. In undirected graphs, there's no arrow on the edge indicating a direction. On directed graphs, there are arrows that indicate direction. When we talk about the edges of an undirected graph, we use set notation to describe those edges. And that's because the edge AB is exactly the same as the edge BA. For directed graphs, however, we use ordered pair notation when we're talking about a given edge because the edge BA, which is shown in the second graph on this page, is different from the edge AB. And when we talk about a directed graph, the first coordinate is the head and the second coordinate is the tail. So this ordered pair here, BA, is uniquely describing the edge that we are seeing from B to A. All right, we have a lot more terminology here, and these things all are going to sound similar, but we'll summarize it at the end. So a walk is a sequence of vertices and edges where edges may be repeated. A closed walk is a walk that starts and ends at the same vertex. A trail is a walk with no repeated edges. A path is a walk with no repeated vertices, except possibly the start and end if it's a cycle. And then we have a circuit, which is a closed trail, and a cycle, which is a closed path. Now that was a lot of terms, but I think it's much easier to kind of think about a summary here. So walks are kind of the loosest constraint, right? We can have repeated vertices and repeated edges in a walk. A trail is a walk, but it cannot have any repeated edges. A path is a further refinement. Not only can it not have repeated edges, it can't have repeated vertices. And then circuits and cycles are simply closed trails or closed paths. So by that we mean it has the quality of a trail or a path, but it starts and ends at the same vertex. And when we're talking in terms of closed trails or paths, we don't count repeating the first and last vertex as a repeat. There can't be repeats in the middle, however, when we're dealing with paths. Okay, let's talk about connected graphs. A graph is connected if there is a path between every pair of vertices. On the other hand, a disconnected graph has isolated components or isolated vertices. A subgraph is a portion of a graph that includes some of its vertices and some or all of its edges. The key idea here is a subgraph is formed by selecting parts of a larger graph. There are, however, several types of subgraphs. A general subgraph is just any subset of vertices and edges. An induced subgraph is formed by selecting a subset of vertices and all the edges connecting them in the original graph. And a spanning subgraph contains all the vertices of the original graph, but possibly fewer edges. So again, let's just look at a couple of examples. On the left, I'm showing a graph. We'll learn in a couple minutes. This graph is called K5. And I'm showing on the right a general subgraph. So it's just a selected number of vertices and edges from that graph. Again, we are looking at on the left at K5, but now we're looking at an induced subgraph. So it's induced because it's a subset of the vertices of the original graph, and it includes all the edges that connect that subset of vertices. And lastly, we have a spanning subgraph, which has all the vertices of the original graph, but not necessarily all the edges. Why is all this important? Why are subgraphs important? Well, they help us in analyzing graphs because often graphs are quite complex and we can focus on subgraphs and learn a lot. This is useful in network analysis where we're analyzing graphs, when we're searching for specific structures like cycles or trees within graphs, or we're working on optimization problems like a shortest distance between two nodes or minimum spanning tree problems. So I mentioned K5 a minute ago. K5 is one of the complete graphs. A complete graph on n vertices, which we call K sub n, is a simple graph that contains exactly one edge between each pair of distinct vertices. So let's look at some of the complete graphs. K1, haven't drawn here, it's not really that interesting. K1 has one vertex and no edges. Some texts show it, some don't. K2 has two vertices and one edge. K3, three vertices and three edges, and so on. Now what you can notice here is that each node in a complete graph connects to all the other nodes. We see that. And the degree of every node is one less than the n value of the graph. So if we're talking in terms of K4, all the nodes have degree 3. In other words, they have 3 edges coming into that node. The graph complement is interesting. A complementary graph, G bar of a simple graph, has the same vertices as G, and 2 vertices are adjacent in G bar if and only if they're not adjacent in G. So you can think of it that way. So what that definition kind of said is you have to think of every possible connection between each of the nodes. And if it's in the original graph, it's not in the complement, and vice versa. Another way of thinking about it is you can look at the complete graph for this scenario. So we've already saw K5. This is on the left, it's a 5-node graph. And K5 would be essentially the sum of the two graphs that I'm showing. And you can kind of see here visually that the complement is the complete graph minus the graph of interest. Now there's a number of ways that we can represent graphs in computer programming languages, and I'm just showing you 3 of these, mostly for awareness. We'll dive into one of them in a little bit more depth. But one way of describing a graph is simply by having an adjacency list for each vertex. So here you can see I'm showing that in a table. For vertex A, we have a list of B, C, and E being the vertices that are adjacent. For B, only A is adjacent. For C, we have A, D, and E as adjacent vertices, and so on and so forth. Another interesting way of depicting graphs is with an adjacency matrix where each vertex is listed across the rows and columns, and the entries in the matrix are 0 if there's not an edge, and 1 if there is an edge. So you have to kind of imagine here that the first row is A, the next row is B, the next row is C, the next row is D, and the next row is E. And same for our columns. First column is A, second column is B, third column is C, fourth column is D, and fifth column is E. And for example, we can see that in the first row, second column, so that corresponds to AB, there's a 1, indicating that there's an edge there. Similarly, in the first column, second row, there is also a 1. That also is indicating the same edge, AB. And if you study this, you'll find that all the edges are described in this matrix. And one final way that we model graphs in programming languages is with an incident matrix. For this matrix, our rows equate to vertices and our columns equate to edges. And each edge is connecting two vertices, and you can see by looking at each of the columns which vertices that edge is connecting. So let's look at an adjacency matrix example. So let's consider a simple undirected graph with 4 vertices, A, B, C, and D, and the edges AB, BC, and CD. So I'm showing the adjacency matrix for that graph. And what I want to show you is there's a couple interesting things we can do. So, for example, if we compute A squared, which we remember from our matrix lecture is the product of A and A, so we do a sum of the products of the corresponding rows and columns for each entry to get each entry. And if we do that, we can see that this matrix tells us the number of distinct paths of length 2 from vertex A to vertex J. So it's just an interesting thing we can do with this adjacency matrix. And I wanted to show you the sort of thing we would potentially do in a programming language to manipulate one of these graphs. Another example, if we have an adjacency matrix, if we add another edge, right? It's quite simply to add an edge between A and D. We have to turn 2 of our zeros to 1s, and you'll see that in the upper rightmost one and the lower leftmost one, which both correspond to the edge AD. So those are just some simple manipulations that we can do of graphs stored in a programming language.